Good morning, students. Myself, Kirtan Kumar TG. Today, I'm going to talk about virtual network embedding problem. So, what is virtual network embedding problem? So, what is the input for this particular problem? See, for example, while solving the virtual network embedding problem, mainly we are going to consider two inputs. One is physical network, and another is virtual network request. So, in this example, we took one physical network and two virtual network requests, VNR1 and VNR2. So both network, one is physical network and virtual network, both are represented in terms of undirected graph. Okay. So weighted undirected graph. Why it is undirected? So there is no direction for the edges, and also each edges are assigned with some weight. That's why it is called as weighted undirected graph. So usually, since it is referred as an undirected graph, the circle represent node and the link represent edges. Okay. And one more thing is, in the physical network, the circle means the node will be belongs to the servers. Okay. For example, in the physical network graph, we are having 5 nodes, namely capital E, capital B, capital C, capital D, and capital E. All these 5 nodes are called as physical server. Similarly, there are two requests. One is virtual network request 1, having the 2 nodes, small e and small b. This small e and small b corresponding to the virtual machine. And similarly, the VNR2, virtual network request 2, we're having 3 nodes, small c, small d, small e, corresponding to the virtual machines for the request number 2. So what are all the numbers on top of the circle? For example, here in a VNR1, on top of the circle or a node A, we return 16. That 16 is corresponding to the demand, CRB demand of the VMA. Similarly, 10 is corresponding to the CRB demand of for the node B. And this 12 represent bandwidth demand between the link A to B. So means what are the values we are going to represent or we are going to see on the virtual network request, that numbers or values will be corresponding to the demand. In the other case, the numbers are the values which is available on physical network, that will be represent available capacity. For example, take the node E, where the node A is nothing but physical server with the name A, having the CRB available capacity of 10 units. Similarly, if I want to establish the connection between A to B, see, there is a connection between A to B, then that A to B is having the bandwidth demand, sorry, not a demand, available demand of 14 units, like that. Okay. So now come to the VNE. So the VNE problem is corresponding to mapping of these two requests, like VNR1 and VNR2 on top of the physical network, is called as virtual network embedding problem. Okay. So I hope it is clear. Means here, in this case, there are two virtual network requests, namely VNR1 and VNR2. VNR1 is having the two virtual machines, namely A and B, with the CRB demand of 16 and 10, and the bandwidth demand of between the two VMs are 12 units. Similarly, VNR2 is also having the 3 virtual machines called nodes with a CRB demand of 10 unit each for the C, D, and E VM. And the link bandwidth demand between C to D is 5 units and C to E is 5 units. Okay, this is like a just explanation corresponding to the graph. Next, The mapping of VNR1 and VNR2 on top of the physical network is called VNE problem. In VNE problem, both physical network and virtual network requests are represented as an undirected weighted graph, as I shown in the previous sheet. The physical network resources are referred as available resources, like VNR, In a physical network, each node is referred as a physical server. In a given diagram, there are 5 physical servers, namely capital A, capital B, capital C, capital D, and capital E, with a CRB of 10, 15, 20, 10, and 10 with a link bandwidth. Okay, next. So actually now if people have a small doubt, like there are 2 requests, which one we need to consider for mapping, right? So actually that mapping of request is vary from the approaches, vary to the author's decision. Like for example, the way how I'm going to solve that problem, based on that one, author will pick the VNR. So for example, either I will pick the first come first serve basis, like VNR1 is arrived first, then I will address the VNR1 request. Once that is done, I will go for the second request, that is VNR2. Otherwise, I will calculate the revenue for the VNRs. For example, 2 requests arrive. For all the 2 requests, I will calculate the revenue. I will pick the least revenue VNR. Then I will map that first. Then I will pick the next least revenue request for the mapping purpose. Okay, so means approach will be vary from person to person and approach to approach. So assume here I pick VNR1 as a first request to map on top of the physical network. While mapping, I need to address for the subject to certain constraints. Okay, simply I can't place VNR1 on top of the physical network. It should be subjected to some constraints. Okay, so we'll in this problem currently we took only 2 parameters, that is CRB and the bandwidth constraint. We are going to validate our mapping. Before mapping, I'm going to check the CRB and bandwidth constraint. Then only if both are satisfied, then only I'm going to map. Okay. So there are other parameters also we can consider as a constraint, like location, quality of service parameters, security parameters, delay parameters, and etc. Okay. So this mapping problem, that is virtual network embedding. Embedding is also called as mapping problem. Okay. This problem can be solved using genetic algorithm approach, heuristic approach, meta-heuristic approach, and MILP approach, where MILP stands for Mixed Integer Linear Programming Approach. Okay, so like this we can solve the problem. Next. So currently, like here we are going to use greedy approach to map the node. Means here I'm not going to simply I'm going to select a random way of selecting the VNR request. Okay, so assume now I want to place the VNR1 request on top of a physical network. Each VNE problem is involved 2 sub-problems, namely node embedding and link embedding. So you need to remember embedding stands for mapping. Okay. So both node and link embedding are called as, or both are NP problems. Okay, it is NP problems. Now, take the first one, node embedding. So as I said earlier, to carry out the node embedding, I want to subject that node embedding to some certain constraints here. So for example, assume node constraint will be written like this. Okay. So in the VNR1 request, we are having 2 nodes, A and B. Assume I pick small a as a first node, means first VM, which has to be mapped on top of the physical server. So if I want to map small a on top of the servers of the physical network, any one server, what I have to do, I need to check the capacity demand of the A. So what is the capacity demand of the A? So in the VNR1 graph, if we saw, Just I will, for your reference, I will show you the values here. VNR1 having two nodes A and B. A node having the demand of 16 CRB unit and B node having the CRB of 10 demand units. Okay, so now demand always must be less than or equal to available capacity of the physical servers. Okay, if this constraint is matched, then only I can place the VM on top of the physical server. Okay, so here small a, that is the VM, demand is 16 units for the CRB. It is less than the physical server available demand of 20 units for the server C. The constraint is matched. What I will do, I will map A on top of the C. So node mapping is successful. This is the conclusion. So here there's a question arise once again. Why we select the node capital C only as a physical server? Why not others? So since I said it is here we are going to use greedy approach, we are going to select randomly. Okay, since I took capital C available demand is 20, so constraint is matched, I can place. So for example, if I took E, assume since I'm picking randomly instead of C, if I took capital A as a physical server, what is the available demand of the capital A? See here. So for the capital A server, available demand is 10. 16 less than or equal to 10, constraint is failed. This condition is failed. I'm not able to perform the node embedding, right? So, but here I took the case where node embedding successful. Next, since A is embedded successful, I will go for the next VM. So next VM is small v. What is the demand of the small v VM? That is 10. Okay, that is 10. Next, 10 is less than or equal to 10. Now, I took the capital A as a physical server to map the VM B. So constraint is matched, right? So since the constraint is matched, what I need to do? Node embedding is successful. So you need to remember, after node embedding is successful, I can go for the link mapping. So one more point you need to remember while performing the node embedding, most of the cases we won't place the same VMs of the same VNR request on top of same physical server. Means if the VMs are belongs to the same virtual network request, then we can't place multiple VMs of the same VNR on top of the single physical network. That condition must be checked. Okay. But VMs of different virtual network requests can be placed on same physical server. If any one node embedding is failed, we can't go for the link mapping. Once again, we need to pick the new request. We need to perform the node embedding. Then only we can go for the link mapping or link embedding. So in our example, both the node mapping are successful. Then I'm going for link embedding. Okay. Now, to establish the link between the physical nodes. So what are the physical nodes here? I need to connect. Since small a is mapped on capital C and small b is mapped on capital A, I want to establish the path between C to A, because in the VNR request, there is a path from A to B, right? There's a single link is there, A to B. So that's why I want to establish the path on the physical network from C to A. So usually to establish the path between the physical servers, we are going to use shortest path algorithm. Like here, we are going to use the digital algorithm. We can use Floyd's algorithm. Any shortest path algorithm we can use, but that must be subjected to the bandwidth constraint. Okay. So for example, in the VNR request, that is in the VNR1 request, the bandwidth demand between the node A to B is 12 units. Okay. So similarly, there is a path from C to A having the bandwidth availability of 12 units, then only we can map. See here, this is the demand. If I want to establish the path between C to A or A to C, both are same because bidirection. There is an available bandwidth demand is 12 units. So I can map from A to B. Assume if there is no possibility, assume instead of 12, if there are 10 units of there, that time I can't take the path from A to C. That time I need to search for the alternative path. What may be the alternative path? When small a is small a is placed on this node and small b is placed on this node, and assume this will be done. That time I can't establish the path from A to C. So what is the another path? See, I can establish from C to E. So there's a 14 units there. I can place the 12 unit here. I can take from E to B, I need to travel, then B to E. So I can, this is the shortest path. If there is no shortest path, A to B is there. From A to C means I need to travel from C to E, E to B, then B to E. Okay, that is the alternative path where I need to establish the link. This is also valid only. Okay. So, but here, since there was 12 units between the A to C, I can directly establish the shortest path from A to C. Okay, next. So this is the bandwidth constraint, what we need to cross-check before placing the link. So bandwidth demand of the virtual link belongs to the virtual network request graph must be less than or equal to bandwidth availability of the physical link paths of the physical network, where these two represent a set. Means it will be corresponding to all the virtual link set. This will be corresponding to all the physical link path. Okay, here bandwidth demand of A to B is 12 and bandwidth availability between C to E is 12. So constraint is matched. So I can do the successful link embedding. Okay. So just one more thing you need to remember is we can use to map a single link, means a single virtual link can be mapped through multiple physical network, multiple physical paths. Okay, means as I said in the previous example, if this C to A path is 10, that time this constraint will be violated, false, failed, right? So that time I need to look for the alternative path. Means so that time I used to travel through multiple physical path, that is from C to E, then E to B, then B to E, to establish the connection between from the C to A node. Okay, so that time how many physical link I consume? 1, 2, 3. 3 physical links are consumed. But here, because constraint is old school, I used only one physical link to map the virtual link A to B. Okay, finally, after doing the link embedding successfully, we need to do the update the physical network resources. Okay, once both the embedding are successful, node and the link, this is the physical network with the updated available demand. See here, on top of capital C, okay, on top of capital C, I placed small a, that is small a VM, which is of the demand of 16 units. So it will become 20 minus 16. So it will become 4, means available CRB at C is 4 now. Similarly, small b VM is placed on capital A server. So small b VM demand is 10 units. So 10 minus 10, 0. So available CRB of the physical server A is 0 now. Since I established the path from C to E, shortest path with the demand of 12 units, so 12 minus 12, it becomes 0. So now between the A to C path, bandwidth availability is 0 only. So this is the updated physical network after successful mapping of VNR request 1. So next, since the request 1 is mapped successfully, we are going to pick for the VNR 2 and we are going to follow the same procedure. So map the VNR2 also, subjected to node embedding, link embedding, followed by the constraint. So that's it with respect to the virtual network embedding problem. So people feel free to post in case of any doubts in the comment section. I will reply to those comments. Thank you guys. Thank you very much.